yet we know its composition. However, while we know that dark matter surrounds us even more pervasively, no scientist has been able to determine its composition. Some 85% of all the matter in the universe is mystery matter. This facility in central Japan was built with the hope of providing the world's first real glimpse of dark matter. In the spring of 2010, NHK cameras were allowed in for the first time to film the X-mass detector as it was being fitted with super-sensitive light sensors called photomultiplier tubes. But why are scientists going 1,000 meters underground to use this device? It's because the thick bedrock shields the equipment from being influenced by any matter other than dark matter. Yoichiro Suzuki of the University of Tokyo calls this facility an underground observatory that will solve one of the universe's greatest mysteries.
この周りもたくさんありますよね。1立方メーターあたり約3000個ぐらいあるんじゃないか。それが大体270キロ、毎秒270キロで飛んでるわけですから、それだけの数のものが我々の体を突き抜けているということなんですね。巨大なそうやっぱり風みたいなのがこう吹いてくるようなね、その風の中に我々はいると。だからそういうダークマターの風の中に我々が立っているんだと。そういうイメージは時々持ちますね。
For a number of years, many scientists have, like Suzuki, postulated that dark matter is a new type of particle called a supersymmetric particle. But evaluating the numerous candidates has proved to be a long and winding road. First, the story of how scientists realized that dark matter even exists. This is the Carnegie Institution for Science in Washington, D.C. Here a party was held to celebrate 45 years of service to the institution by a pioneering female scientist.
National Medal of Science and other things. You now have a Carnegie Service pin with a ruby.
Vera Rubin, age 82.
One of them involves Dave. Many more people.
It was Rubin who released to the world the data that served as the starting point for the search for dark matter. Fascinated by the stars since childhood, in high school she began to cast her thoughts seriously towards the cosmos, using a homemade telescope. In college, she confidently set her sights on becoming a professional astronomer.
These are special pictures because most of them have been...
Her research topic involved gauging the velocity of stars within various galaxies. The Andromeda Galaxy, for example. Hundreds of billions of stars swirl around its center. Rubin devised a way to derive velocities for the stars marked with black dots in this image. Galaxies outside our own are so distant, we can't actually see their individual stars moving. But if the wavelengths of the light from those stars are analyzed, the star's velocities can be determined indirectly.
Let me show you what it looks like, what you get from a telescope. This is a spectrum of an object, and from this we can get an exact measure of how much the object is moving. I guess most people know that if you have a whistle or an airplane or something is flying, something is moving fast past you, it will seem to change its radiation in the optical sense. So stars do the same thing.
Rubin's observations made use of the well-known phenomenon of the Doppler effect. For example, as a train approaches, its sound travels smaller distances, a shrinking sound wavelength, heard as a rising pitch. As it pulls away, the opposite occurs, longer sound waves and a falling pitch. A similar phenomenon occurs with light. The light of an approaching object has a shrinking wavelength, so it appears bluer than its true color. As the same object recedes, wavelengths increase, and the object looks redder. Using a similar logic, Rubin determined the velocities of stars by measuring changes in light wavelength. The data, however, led her to a startling conclusion. The stars were moving at much faster velocities than predicted. So what was keeping these stars and other objects in their galaxies, instead of being flung out of them? The data could only be explained by the existence of something invisible, with enough gravitational force to keep the stars anchored to their galaxies.
There had to be much, 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 much more matter farther out than anyone had ever expected. And if you do the arithmetic, it's pretty simple.
This discovery is what brought dark matter to the world's attention for the first time in 1970. However, the suggestion that the galaxies contain large quantities of an invisible substance drew fierce criticism from the scientific community.
No one believed it, or the people we spoke to would tell us that you can't do it, the data aren't good enough. The person next to me was a rather great astronomer, and he spent the whole evening telling me why I couldn't do what I did, and I don't know how good those data were.
Despite this cold professional reception, Rubin persevered, undaunted. In applying to graduate schools, she had encountered rejection simply because she was a woman. She says this experience helped her later in dealing with colleagues' prejudices. By the end of the 1970s, she had charted the movements of stars in more than 100 galaxies. Her results proved that in all these galaxies, stars were moving at faster velocities than had been predicted. These observational data definitively established the existence of an invisible substance acting on the stars.
So this was the first time in astronomy, I think, that people had really inferred the existence of something from gravity alone, without actual evidence from light, from photons. So it wasn't a rare thing. It wasn't just here and there. It was in every galaxy. And we needed to understand that, what it was, where it came from, in order to make our whole picture of galaxies.
What was the source of this gravitational force holding a galaxy together? Starting in the 1980s, the challenge of dark matter was taken up by a legion of scientists. The first hypothesis that attracted many scientists was that dark matter was actually made of numerous dark stars, invisible to observation with telescopes. David Bennett of the University of Notre Dame is one of those who used to believe that dark matter is composed of dark stars that do not emit light. When most people try to imagine a star that does not emit light, they are likely to think of a celestial body so small in mass compared to a radiating star that it's more like one of the planets of our solar system. By the mid-1980s, however, scientists knew that the universe does include many dwarf stars and black holes and other extremely massive objects that do not emit light but may exert powerful gravitational forces. Establishing that dark matter is actually comprised of dark stars would require proving the existence of massive dark stars in numbers far greater than radiating stars. The conceptual tool Bennett decided to apply was gravitational lensing. It was Albert Einstein who first proposed gravitational lensing in 1936. Instead of traveling straight, he theorized, light from a star would be bent by a massive object exerting a powerful gravitational force. So if a dark star cut across the path of a radiating star, the light from the radiating star would temporarily appear to increase as the dark star passed, before returning to its original brightness.
We can consider this this little flashlight to be a background star, and then this glass will represent the foreground object, and as it passes in front, it distorts the image, and the effect of that distortion is that we see the object appear to get brighter and then dimmer again.
The plan was simple. Find stars that get brighter and then return to their original brightness. If dark matter was indeed massive dark stars, a little perseverance should suffice to prove that. A colleague of Bennett's thought this plan too simple.
Later on, when he wrote something about it, he attributed my enthusiasm due to the fact that I didn't have any observing experience and didn't know how hard it would be. And I thought that was just great, because here, was a case where you could do a measurement and you either found the dark matter or you ruled it out.
Bennett's idea instantly attracted worldwide scientific attention. He rapidly assembled a team of 25 scientists from 6 nations to join the search for massive dark stars. The team trained a super-sensitive telescopic camera on a region that they had divided into 82 sectors for analysis. They then made daily observations of any changes in the brightness of more than 10 million stars. After 3 years of observations, Bennett's group discovered a phenomenon that brought them even more recognition. The science journal Nature carried photos of a star that flashed violently bright, then subsided. Researchers around the world were thrilled by this definitive proof of the existence of massive dark stars. Over time, however, the idea that dark matter phenomena were explained by dark stars gradually lost support. In 7 years of research, Bennett and his colleagues discovered no more than 13 dark stars. A whole chorus of critics insisted that for dark stars to account for dark matter, more than 100 such stars should have been discovered. Bennett and his team had ended up proving, ironically, that dark stars alone could not be the source of those powerful gravitational forces.
But it could be that some galaxies also form a lot more of these brown dwarfs than others do. So that's a possibility. It might be a little bit difficult to tell, but I think, you know, that the vast majority of the dark matter has to be in some other form.
Back when Bennett was hunting for dark stars, another researcher was taking a wholly different approach to identifying the composition of dark matter. Mitsuhiro Nakamura of Nagoya University. His field is particle physics, which had developed rapidly in the latter half of the 20th century. He started from the premise that dark matter is an elementary particle. Since ancient times, scientists have been searching for new elements. In the 1970s, there had been a recognized list of particles making up all matter. There were the electron and 6 types of quark and other particles. They were held together by exchange particles, such as the photon and the gluon. It was thought that all the matter in the universe could be described as various combinations of the 25 particles on this list. For example, protons are comprised of 2 up quarks and 1 down quark, held together by gluons. Protons and electrons, bound by photons, make up hydrogen. The individual who compiled that master list of particles, a co-winner of the Nobel Prize in 2008, was Toshihide Masukawa. The general theory of particle physics worked on by Masukawa and others is referred to as the Standard Model. The general opinion at the time was that all physical phenomena in the universe must be explainable by the Standard Model.
かなり高い精度の桁で予言ができる、で合ってくる。そういう過程で、皆さんが標準理論というような言い方するようにまで完成を見たわけですね。
Nakamura, on his quest to identify the mysterious dark matter, was convinced that it would be found somewhere on the list indicated by the Standard Model. Narrowing the list down to possible candidates for dark matter did not take very long. The first to go were the components of normal matter, such as hydrogen, namely the up quark, the down quark, and the electron. Then the particles that bind the others together, the gluon and the photon. Finally, Nakamura eliminated the most short-lived, unstable particles. What were left were only 3 types of neutrino. It was known that the universe contains an immense number of neutrinos, and that neutrinos have the ability to pass through other matter, so they were highly suitable candidates for dark matter.
ニュートリノっていうのはものすごい数宇宙空間に存在していると考えられてたわけですね。 でその数は、実際に存在している原子の数億倍の個数ですね。だから個数代からいくともう圧倒的にニュートリノの宇宙と考えてよかった。そのニュートリノに少しでも重さがあれば、要するに普通の原子の数億分の1の重さがあれば、原子なんかよりも圧倒的にニュートリノが重いということで、ダークマターの候補となり得たということですよね。
If an individual neutrino has more than a certain mass, the dark matter problem is solved. So Nakamura and his colleagues, using devices they built themselves, started measuring the mass of various neutrinos. At that time in Japan, another neutrino experiment was also taking place. A research team at the University of Tokyo was using a gigantic device called the Super Kamiokande. Fitted with over 10,000 optical sensors, the Super Kamiokande successfully measured the precise mass of neutrinos. The results showed that even the heaviest of the 3 candidate neutrinos did not possess 1/100th of the mass postulated by Nakamura. Neutrinos were now disqualified as potential dark matter.
自分たちが絶対これだという確信を持って世界で初めて発見するぞっていう勢いでやってたわけですよね。正直言って、残念というか。
So now both dark stars and neutrinos were out of the running for dark matter. There was no shortage of alternative theories. But by the end of the 20th century, the search for dark matter was foundering. Vera Rubin had been ahead of her times in championing the existence of dark matter. When scientists lost the trail of dark matter, she was in her 70s and still a stargazer.
I could see them from my window. I didn't have to leave my bed. And really, after a while, it was more interesting to watch the stars than to go to sleep.
Continuing her professional observations of the heavens, Rubin tried to turn scientists' attention once more to dark matter. She insisted that fresh data were needed.
I didn't know if we were missing something, if there was something I had not done that should be done. I mean, it was certainly initially, it was so strange and so unexpected that I felt that I better keep going.
In the 21st century, just as Rubin had wished, new data came flooding in.
3, 2, 1. Main engine start.
In 2001, NASA launched WMAP. It was designed to provide a precise map of the universe's microwave background radiation. From the varying intensity of that radiation, it could determine temperature distributions throughout the universe. From those patterns, it could further calculate the total mass of all the matter in existence. The results were astonishing. If one adds together the mass of all the ordinary matter in all the galaxies and interstellar gases observed so far, it amounts to no more than 15% of the total matter in the universe. Here was confirmation that 85% was comprised of an unknown substance. It transpired that dark matter not only helped form our stars and galaxies, but ultimately was essential to the origin of life. Naoki Yoshida of the University of Tokyo has created a computer simulation of the universe in the moments just after its creation. He found that without dark matter, even if one assumes that the universe is born, nothing comes of it. The Big Bang is said to have happened 13.7 billion years ago. At that moment, many kinds of matter were created. If there were no dark matter, and the universe consisted purely of ordinary matter, how would things have developed? Given a billion years, or even 10 billion years, matter cannot coalesce by the force of its own gravitational attraction, and not a single star shines in the heavens. If stars cannot form, then there will be no oxygen or carbon, those elements of life. In this simulation, however, along with ordinary matter, dark matter exists. As soon as the universe is born, the gravitational power of dark matter helps ordinary matter take shape. Eventually, a sufficient mass is built up so that 300 million years later, the first star in the universe is born. Dark matter even supports the formation of the galaxies, which start taking shape a billion years after the Big Bang. Later, the countless galaxies that have formed are distributed in large-scale structures that resemble bubbles or nets. These structures would also have been impossible without the gravitational force of dark matter. All in all, without dark matter, the universe as we know it could never have formed.
基本的には何も起こらないんでしょうね、おそらくダークマターがないと。こういう構造を作るにしろ、星や銀河を作るにしろ、やはりその元となるもの、物質を集めるわけですから、その物質を集める時にはダークマターによる重力がないと、そのことそのものも起こらないということになると思います。
In one of his simulations, however, Yoshida found something that might help to get a fix on dark matter. He determined that if dark matter plays a key role in forming stars and galaxies, a mass tens to thousands of times that of a hydrogen atom would be consistent with the type of heavy particle dark matter would have to be. This was the conclusion indicated by the combination of Yoshida's simulations with other scientific data.
軽いとそのお互い固まることができないですね。いくらそのダークマター同士に重力が働くといっても、軽いとビュンビュン飛び回るわけですから、小さな塊を作ってじっとしていることができない。重かったために宇宙が始まった頃、宇宙がもっと若かった頃にはそのダークマターの分布、散らばり具合が非常に、塊をいろんなところで作っているような状況になっていたんだと考えられています。少し重い元素、そうですね、例えば鉄とか、ウランとか、ああいう重いもの、重い元素と同じぐらいであってもいいだろうと考えられています。
So what could this candidate particle be, with a mass tens to thousands of times that of hydrogen? It had never been found anywhere. A clue to the composition of dark matter appeared from a completely unexpected source. Pierre Ramond is a theoretical physicist. His forte lies not in observation or experimentation, but in using pure mathematics to uncover the laws of physics.
Presumably, if you were to write a closed form formula like this, you would put this to some power. It's fascinating that there are always simple answers to complicated questions, and that is something that which never ceases to amaze me.
One of Ramond's proposed improvements was an important attribute that he said was missing from the Standard Model, namely supersymmetry. Supersymmetry turned out to be related to dark matter in an unexpected way. What exactly is supersymmetry? This highly mathematical concept is difficult to explain to non-experts, so Ramond likes to use the following illustration.
Okay, so you see me waving my right hand, and here in the mirror, if you look in the mirror, you will see that it looks like I'm waving my left hand. Okay, so imagine I'm a particle, and I'm like this, and then whatever this person is looking on the other side is the supersymmetric partner of this. But now, okay, Francisco, please, if you put this mirror.
Ramond deploys another mirror.
Okay, so this way, yes, that is fine. Come closer. Yeah, that is perfect. So now, if you look at this mirror, you will see that I am back to waving my right hand. So this is me. This is my anti-particle, and this is back to me, except I've moved a little bit. And in some sense, the analogy would be that you make two supersymmetry transformations, and it is like you have moved a little bit.
There is one reason in particular why Ramond now thinks supersymmetry important to dark matter. It could provide the solution to a mathematical deficiency in the Standard Model that had been pointed out for many years. In the Standard Model, one of the calculations yielded a value of infinity, a meaningless result. When the theory is augmented with supersymmetry, however, the infinity disappears.
So therefore, that conceptual problem in a Standard Model can be actually solved by adding supersymmetry to the model. Okay?
Using the hint provided by supersymmetry, Ramond is now attempting to derive ultimate laws of physics that will go beyond the Standard Model. But his argument has hit a snag. He now has to establish the existence of mirrored versions of the particles listed in the Standard Model, a corresponding list of supersymmetric particles. With not a shred of evidence that such particles exist, he has reached the limits of what theory can do. Ramond's mathematical refinements, however, have suggested to some researchers that dark matter may in fact be a supersymmetric particle.
The idea here is that you get a tight constraint from could have been destroyed.
One of them is Hitoshi Murayama of the University of Tokyo. He points out that if the dark matter sought by astronomers and the supersymmetric particles conceived of by theoretical physicists are actually the same, then a whole variety of outstanding problems will be solved simultaneously.
もともとダークマターっていうのは天文の観測から発見されてきたものなわけですけれども、ヴェラ・ルービンが銀河の中の星やガスの運動を見る。でそれを説明するためにはダークマターがなければいけない。つまり大きなものを見てダークマターが必要だという話になってきた。そ それから素粒子の分野ではどんどんものを小さく小さく分けていって、原子があり、中に原子核があり、陽子があり、光譜があり、ずっと詰めていくとどうもそれ以外に超対称性ってなきゃいけないんだという話が出てきたと。つまりダークマターというのが超対称性粒子じゃないかと、大きなものを見ていくっていう天文学と小さなものを見ていくっていう素粒子物理学でなぜか同じ答えが出てきた。これはやっぱりすごいことですよね。
The latest supersymmetric models yield a high probability that supersymmetric particles would include one that is several tens or even thousands of times heavier than hydrogen. As the computer simulation of the universe's evolution showed, such a particle would be a perfect candidate for dark matter. Pervading both us and the material world we live in is a huge amount of invisible dark matter, in far greater quantities than the visible matter we are used to seeing. An aspect of reality so strange, one can scarcely believe it exists, and yet its existence is beyond doubt. Currently, research teams around the world are competing in the search for dark matter. One specific goal, the discovery of supersymmetric particles. The best funded of these efforts is conducted by the European Organization for Nuclear Research, CERN. CERN is using its Large Hadron Collider, the world's largest particle accelerator, to smash protons experimentally. In this huge device, 9 kilometers in diameter, they recreate the high-energy conditions that obtained just after the Big Bang, when supersymmetric particles may have been created. The goal is to produce supersymmetric particles artificially. John Ellis has been conducting research at CERN for nearly 2 decades. He strongly supports supersymmetric particles as candidates for dark matter, and he's positive that they will be discovered at CERN. But even if, hypothetically, you could create a supersymmetric particle, how could you confirm the existence of something that is invisible? Ellis contends that if you meticulously track energy flows just before and after proton collisions, you will be able to prove the existence of these invisible entities.
So often they make collisions where a lot of particles come out on one side, a lot of energy. And then usually that energy is balanced out on the other side. And so the energy 1 is approximately the same as energy 2. Okay. This is what normally happens. Now, when you have dark matter, you would have, in addition, particles that you don't see. Okay? So it would carry away invisible energy. In that case, the 2 energies would not balance.
In a collision, roughly the same amount of energy is discharged above and below the collision path, so the total energy balances out. But when invisible dark matter is created, the balance is compromised, and the energy does not equalize. That would be considered proof of the presence of dark matter. At CERN, they have already observed some 3 trillion collisions, compiling a massive amount of data. But at present, they still have found no proof of the existence of dark matter. The search for dark matter is heating up all over the world. Nowhere are expectations greater than for the research team in Japan. XMASS began operating in April 2011. There are two reasons why it has attracted such high expectations from around the world. One is that this is a unique device for detecting the supersymmetric particles that are thought to comprise dark matter. It is filled with liquid xenon that has been cooled to minus 100 degrees Celsius. Xenon was chosen because of a particular feature. Its atoms weigh about 130 times those of hydrogen. In other words, about the same as the predicted weight of the supersymmetric particles.
やはりダークマターの質量とそのキセノンの質量が大体同じぐらいではないかと、そういうふうに予想しています。同じぐらいの粒子が当たりますと、そのエネルギーがですね、非常に効率よく移動するんですね。ですから効率よく検出ができる。
Suzuki's hypothesis can be illustrated with the following analogy. Dark matter is all-pervasive. Even when it enters the xenon, most of the time, nothing will happen. But on very rare occasions, some dark matter will hit a xenon atom and move it. Since their mass is about the same, the energy of the first atom will be transferred to the second, as in a collision of billiard balls. That observable energy transfer will prove the existence of dark matter.
Dark matter があるっていうのはもう本当こう10年以内ね存在は明らかになっている。その正体はまだ明らかになっている。それには直接反応を見て直接捕まえてやってで性質を明らかにしてやる。それが非常に大事だ。
Scientists also have high expectations for the array of supersensitive optical sensors surrounding the liquid xenon inside X-mass. These sensors, called photomultiplier tubes, were specially developed to detect the minuscule amounts of light released by the xenon atoms impacted by dark matter.
その我々の新しい測定器の幹部はですね、今まで世界中でいろんなダークマターの探索っていうのをやられてるんですけども、それに比べて50倍ぐらい、50倍から100倍ぐらいだからここで本当にそういうダークマター自身に肉薄できて、そういう証拠がね得られれば非常に嬉しいと思います。
The research team is monitoring their 642 sensors around the clock. It is estimated that some 2,000 units of dark matter enter the device every second. And the probability that one will impact a xenon atom ranges from about once every few days to once every 10 days or so. Researchers thus estimate that within a year at the earliest, they will be able to identify dark matter. "40 years ago, Vera Rubin pointed to the presence of something in the galaxies that exists but cannot be seen."
Here are some of the books and the little globes. Yeah, the ones I like the best are these. They're pretty old. I've forgotten.
You can take it out and show us. Yeah.
No one is more surprised than she that the contemporary debate over dark matter, which began with her observations of the cosmos, now extends to supersymmetry and the search for the ultimate laws of physics.
This is our sun.
Rubin cautions that in the face of such mysteries, scientists should always proceed with humility.
I'm a little skeptical about some of the models of the universe because you're going out so far. But in a sense, I mean, that's how science goes. You do the best you can. You make the best suggestions or guesses or whatever you want to call them. And And there's probably some right in them, and there's probably some wrong in them, because we're not very good at imagining very different things.
The search for dark matter began with the persistence of a single researcher. In their effort to resolve the riddle of dark matter, bound up as it is with the search for supersymmetric particles, what new horizons will scientists behold? Will their pursuit give rise to further mysteries?
Let me show you what it looks like, what you get from a telescope. This is a spectrum of an object, and from this we can get an exact measure of how much the object is moving. I guess most people know that if you have a whistle or a airplane or something is flying, something is moving fast past you, it will seem to change its radiation in the optical sense. So stars do the same thing.
Rubin's observations made use of the well-known phenomenon of the Doppler effect. For example, as a train approaches, its sound travels smaller distances, a shrinking sound wavelength, heard as a rising pitch. Yet we know its composition. However, while we know that dark matter surrounds us even more pervasively, no scientist has been able to determine its composition. Some 85% of all the matter in the universe is mystery matter. This facility in central Japan was built with the hope of providing the world's first real glimpse of dark matter. In the spring of 2010, NHK cameras were allowed in for the first time to film the X-mass detector as it was being fitted with super-sensitive light sensors called photomultiplier tubes. But why are scientists going 1,000 meters underground to use this device? But evaluating the numerous candidates has proved to be a long and winding road. First, the story of how scientists realized that dark matter even exists. This is the Carnegie Institution for Science in Washington, D.C. Here a party was held to celebrate 45 years of service to the institution by a pioneering female scientist.
National Medal of Science and other things. You now have a Carnegie service pin with a ruby.
Vera Rubin, age 82.
One of them involves Dave. Many more people.
It was Rubin who released to the world the data that served as the starting point for the search for dark matter. Fascinated by the stars since childhood, in high school she began to cast her thoughts seriously towards the cosmos, using a homemade telescope. In college, she confidently set her sights on becoming a professional astronomer.
These are special pictures because most of them have been...
Her research topic involved gauging the velocity of stars within various galaxies. The Andromeda Galaxy, for example. Hundreds of billions of stars swirl around its center. Rubin devised a way to derive velocities for the stars marked with black dots in this image. Galaxies outside our own are so distant, we can't actually see their individual stars moving. But if the wavelengths of the light from those stars are analyzed, the star's velocities can be determined indirectly. It's because the thick bedrock shields the equipment from being influenced by any matter other than dark matter. Yoichiro Suzuki of the University of Tokyo calls this facility an underground observatory that will solve one of the universe's greatest mysteries.
この周りもたくさんありますよね。1立方メーターあたり約3000個ぐらいあるんじゃないか。それが大体270キロ、毎秒270キロで飛んでるわけですから、それだけの数のものが我々の体を突き抜けているということなんですね。巨大なそうやっぱり風みたいなのがこう吹いてくるようなね、その風の中に我々はいると。だからそういうダークマターの風の中に我々が立っているんだと。そういうイメージは時々持ちますね。
For a number of years, many scientists have, like Suzuki, postulated that dark matter is a new type of particle called a supersymmetric particle.